Across the education system, a massive number of adolescents fail to succeed in advanced algebra. This is a predictable, systemic pattern that appears across demographics. When researchers trace the origin of this failure, they reliably find it rooted in a weakness, in one specific cluster of mathematical concepts: rational number reasoning. Current standardized testing models hinder instruction in this area by relying almost entirely on multiple-choice snapshot testing to measure student progress. These tests capture the recall of rote procedures at a single point in time, failing to measure how complex mathematical concepts gradually develop in a student's mind over time. To accurately map that development, mathematics education researchers use an empirically validated model known as a learning trajectory. This diagram illustrates a learning trajectory, which functions as a conceptual corridor. Rather than testing a final destination, the trajectory maps the intermediate cognitive states a student encounters, documenting the landmarks they must reach and the structural misconceptions they must resolve. Shifting from snapshots to trajectories changes the purpose of an assessment from grading a final answer to pinpointing a student's exact coordinates in their cognitive development. Traditional mathematics curriculum operates in a strict linear sequence. Counting leads to addition, which leads to multiplication, then fractions, and finally ratios. This linear model compartmentalizes mathematical ideas that actually share the same cognitive bedrock. Research synthesis by Jerry Confrey reveals that multiplication, division, fractions, and ratios are parallel outgrowths of a single primitive cognitive construct. That construct is equipartitioning, the cognitive behavior aimed at producing equal-sized groups from a collection or equal-sized pieces from a continuous whole. In its earliest stages, equipartitioning is the formalization of fair sharing. Think of a young child carefully dealing out a collection of physical objects evenly to a group of friends. Establishing a one-to-one correspondence to ensure everyone gets an equal share provides the literal foundation for advanced rational number reasoning. Recognizing equipartitioning as the foundation requires a total re-engineering of how we measure a student's readiness for algebra. To accurately map this trajectory, we must first parse the symbolic expression a over b into three distinct mathematical meanings. The first meaning is a over b as a fraction. This one-dimensional number line models the fraction, where we measure a quantity against a single shared unit of 1. The second meaning is a over b as a ratio, which defines the relative size between different quantities, such as miles and hours. This coordinate plane models the ratio. 12 objects for 3 children sits at point 12, 3. Tracing the vector down to 4, 1 reveals the equivalent relation of 4 objects per child. Ratio equivalence is a relation preserved by a scale factor, not a fixed point. The third meaning is a over b as an operator. Here, the expression acts as a composition of factors. The object shrinks as it is divided by b, and then immediately stretches as it is multiplied by a. A student cannot master abstract algebraic concepts if they cannot effortlessly distinguish between these 3 spatial and operational dimensions. The equipartitioning trajectory tests these meanings across 3 escalating problem spaces, starting with Case A, collections. Case A involves sharing a collection of discrete objects, like 12 items among 3 children. The student may view the result as many to 1, objects per child, or as many as 1, seeing a distinct chunk of objects. The many to 1 perspective primes the brain for ratio reasoning, while many as 1 establishes the foundation for partitive division. Transitioning to Case B involves sharing a single continuous whole, which introduces emergent mathematical properties. In Case B, a vertical 2 split might be intersected by a horizontal 3 split to produce a composition of splits. This physical transformation helps students overcome an additive misconception, predicting 5 shares, to realize a multiplicative conception of 2 times 3 equals 6. The physical actions of cutting or folding a real object instill cognitive symmetries that dictate how a student perceives equivalence. The geometry of splitting continuous shapes directly writes the mental software required for the formal rules of arithmetic. Case C is the highest level of the trajectory, sharing multiple wholes among multiple people, where the people outnumber the wholes. This creates extreme cognitive demand, requiring students to manipulate mixed referent units and covariation simultaneously. Facing 4 pizzas for 5 people, students often revert to a cased A strategy, breaking the wholes down into benchmark fractions like quarters to deal them out. While they can physically deal the parts, students often experience profound difficulty naming the new referent unit of their result. Resolving this naming struggle leads to the ultimate generalization of the trajectory, understanding that a shared among B equals A over B per person. Teaching this generalization as a mere assertion, without requiring students to negotiate intermediate physical steps, creates an empty pseudo-concept that shatters under the pressure of algebra. To practically measure this invisible cognitive architecture, we must build diagnostic assessments focused on the learning trajectory. One such task targets level 12, equipartitioning 4 whole pizzas among 5 friends. The rubric for this diagnostic does not simply grade binary correctness, it isolates specific cognitive barriers. Full credit requires accurate geometric partitions and explicitly naming the correct referent unit, such as 4/5 of one pizza. This hand-drawn solution shows a student attempting to split a circle into fair shares. The student used parallel cuts, faking the shares and revealing a documented shape misconception in their spatial reasoning. This drawing functions as a highly specific coordinate on the learning trajectory, revealing exactly where the student's spatial logic stalled. Another partial credit code identifies the tendency for students to make n+1 cuts when trying to create n parts. Isolating these precise misconceptions allows teachers to execute targeted instructional interventions rather than reteaching a whole unit. This chart visualizes the complete architecture of rational number reasoning. Equal partitioning sits at the bottom center as the foundational bedrock. Tracing connections upward reveals how mastering the pizza problem supports the parallel pillars of ratio, decimals, and advanced algebraic volume. Failing to install this primitive bedrock in early adolescence guarantees structural collapse in advanced mathematics later. By embracing empirically supported learning trajectories, we stop punishing deficits in procedural memory and gain a precision instrument for engineering higher-order cognition.